All right, so let's continue our discussions regarding the MOSFET operation. Last lecture we had said that if you apply, let's go back to this particular diagram, the one before that. If you apply, we have applied 2 volts here, and we are saying threshold voltage is 1 volt, and therefore, if you apply 1 volt to the drain, what you end up getting is that next to the drain, the channel gets pinched off. Pinched off in the sense that the inversion charge becomes very small. And then we were talking about, and that is the point at which the current also saturates. And we were then discussing what happens if you go beyond 1 volt here. And so the idea was that as you go beyond 1 volt to 1.5 volt here, and the pinch off point, it moves towards the left here. The pinch off point here moves here. So note that if this is 1.5, the pinch off is occurring when the voltage in the channel is 1 volt. Right? The pinch off occurred when the voltage in the channel was 1 volt. So if this is 1.5, then the voltage here is 1.5, somewhere would be 1.4, 1.3, 1.2 and all that, and eventually it will reach 1. And at the place where the channel voltage reaches 1, I will get a pinch off according to this expression. Cox, VGS minus VTHN minus Vx. Vx is the voltage in the channel. If VGS is 2, threshold voltage is 1, 2 minus 1, 1 here. So wherever Vx is 1, we'll get a pinch off here. So the pinch off occurs here at this particular point. Now, I've been saying that pinch off doesn't mean that the carrier density is 0. There are carriers here, but at this point is pinch off occurs, and beyond all this is pinched off. There is no channel in the sense indicated by this particular equation here. So this is all region where the carrier density is very small. These are very high field regions here. So what happens is whatever carriers come from here, they enter a high field region and they are swept away by the field into the drain here. So it's a high field region, whatever enters. So try to recollect something like a collector. From the emitter you inject something into the base. The carriers diffuse from the emitter end to the to the end of the base, and once they reach the base collector junction, there's a high field. We normally keep base collector junction reverse bias. There is a high field, and the field sweeps the carriers into the collector. So something similar is happening here. Starts from source, reaches here. The moment it reaches here, there's a high field region which sweeps it up into the drain. Okay. So the pinch off point then moves over here at this particular point here. Into the channel here. Earlier it was here, now it is moving here. All right, so the consequence of this is that when we apply 1.5 volt, there is a, earlier the pinch off region was a point. We said it's at this particular place. Now the pinch off is a region of a certain length delta L. This is voltage here is 1.5 and this is 1 here. So effectively what we can say is that my channel length, where the channel exists here, is no longer L, but it is L minus delta L. Effective channel length is, because this is a high field region here, as I said, whatever enters, whatever reaches here is swept into the drain here. So this does not contribute to or does not affect the current to the first order approximation here. It is here, this is where the channel is. So the channel length, effective channel length is no longer L, but it is L minus delta L. Okay, and as I apply even higher voltages here, then this point will shift further and my effective channel length will become even smaller. So what we are talking about in a MOSFET is the phenomena of channel length modulation. That as I apply more and more drain voltage here, the effective channel length decreases here. Now you can recall, what does this correspond to in a bipolar? As I apply higher and higher collector bias, what happens? The effective base width, if you recall, reduces, and that was the cause of early effect. The fact that current in active region keeps increases a little bit. So it's the same phenomena here. As I apply here, the effective channel length decreases here, and as a result of which the current increases a little because of the voltage here. Because earlier my channel was of if the channel is longer, the current is smaller. If the channel length is smaller, the current is larger here. So effective channel length has become a little smaller here, and as a result of which the current increases. So remember, saturation occurs when the voltage at this point reached 1 volt. Beyond from 1 to 1.5 and 2 and all that is happening is that delta L is increasing, effective channel length is decreasing, and the current increases a little with voltage. So this was the point where we said sort of a pinch-off occurs, and beyond pinch-off, saturation occurs, and beyond pinch-off, the current, as you can see here, is slightly increases here. And we model that by saying whatever was the current at this particular point, let's say this is ID sat. So the current here increases as 1 plus lambda times VDS, increases with the voltage here, slight increase in voltage. Because what is the voltage doing? The extra voltage is decreasing the channel length and causing a increase in current here. Okay, so so the current in the saturation region has is not completely flat. It has a small dependence on VDS, and so the current is whatever this expression we'll see later on will be 1 plus lambda times VDS, and 1 plus lambda or 1 over lambda is like the early voltage. If you recall, for the collector current, we had an expression, some expression here, exponential VB by VT and all that, and we had 1 plus collector emitter voltage divided by VA, early voltage here. So here we have 1 plus VDS divided by 1 by lambda, and 1 by lambda then is like the early voltage for a MOSFET here. Okay, so this is the parameter lambda. 1 over lambda is what will decide as the output resistance of my MOSFET here. Just like early voltage used to decide the output resistance of a bipolar, 1 over lambda will decide that for a MOSFET. All right, so I was telling that there is a high field region here. You can note, these are results from simulation, and you can see it is plotting the field as I go from here to here. So note what happens to the field here. Field is all, don't worry about the direction. So you can see here, as you reach this drain end here, note how high the field goes here. High field region here, next to the drain. Simulation results showing very high field here. And then, of course, as you enter the drain, you enter a low resistive region here, a high conductivity region here. The field again drops back to very low values here. So this is the point that we are talking about, is the pinch-off region here, next to the drain here. Very high field here. All right, so so as I said, this is the basic operation of how a MOSFET works. Okay, so now we have to basically, understanding is, qualitative understanding is one thing. We would like to know how to use the MOSFET, how to deploy it in circuits. And for that, we need models. We need the mathematical relationship between the currents and voltages here. So the first thing, we've already noticed that threshold voltage is an important parameter. So again, I'm going to write down equations. I'm not going to derive. I'm not going to justify those things here. So the threshold voltage of a MOSFET can be written in this particular form. So threshold voltage, remember threshold voltage is a point. Once you cross threshold voltage, you start getting a strong channel here, strong inversion. Okay. So if you want to get significant current from your MOSFET, you'll have to bias gate to source voltage has to be larger than the threshold voltage. Okay. So threshold voltage is, there is a part VTHN0 which is bias independent. It doesn't depend on the bias. So it's a parameter. Gamma is a parameter called body parameter. You can note that if this is square root of voltage, this also has to be square root of voltage. Square root 2 phi f plus VSB minus square root 2 phi f here. All right, all these are for you at this point. What is this 2 phi f? What is this gamma? We will not bother. Where does it come from? All these equations, where does it come from is not the subject of interest here. What is important is the following. Threshold voltage has two parts to it. One part is a constant part. The other part is dependent on the source to body voltage. So you can alter the threshold voltage of a transistor by altering the source to body voltage. This is also a constant. 2 phi f is a constant. Gamma is a constant. And VTHN0 is a constant. So depending on the technology that you're using, we've been talking about 180 nanometer or 130 nanometer and all that. So once you use a particular technology, these parameters will be available to you. VTHN0 will be given to you. Gamma will be given to you. 2 phi f will be given to you. So all these are available. So from a circuit's point of view, as a circuit designer, what you need to know is that if I short source and body, VSB goes to 0 here, and my threshold voltage is a constant, is bias independent. But If you want, you can take advantage of the fact that source to body voltage is also available to you, and you can use it to an advantage in some cases where you may want to increase the threshold voltage. So if you want to increase the threshold voltage, make the source to body voltage positive. So if the source is ground, make the body negative, and thereby you can get a higher threshold voltage. If for some reason you want a higher threshold voltage, you could do that. Or if you want a lower threshold voltage, well, you make the source to body voltage negative. But note that if this is 0, and to make source to body voltage negative, you will have to make body positive. And if you make body positive, then this is a PN junction, you're forward biasing the PN junction. So you have to be very careful how much forward biasing of the PN junction you do. Because if you forward bias it too much, if you start approaching 0.4, 0.5 or 0.6, you'll start getting a lot of current. And in a normal operation of a MOSFET, we don't want this source body diode to be on. All right, so this is not in our interest. Our interest is, when I'm using a MOSFET, our interest is in this current here, channel current here. Any extra current, any other current is, unless you want this current to flow, okay? But most of the time, what we are interested when we are using a MOSFET is this current here. And so our interest is that all other currents should be negligible. So you can reduce the threshold voltage, but you are in sort of a danger territory. If you're not careful, you may bias the source body junction too much and start getting currents here into the source here, unwanted currents in these source here. Okay, so but note that this parameter, as a circuit designer, source to body voltage may be available to you. You can use that to tune your threshold voltages. That possibility is there. So threshold voltage, then one parameter which is independent, technology parameter. Gamma is also a technology parameter. 2πf is also a technology parameter. I'll come to, I think I'll have slides later on. When I say these are constants in the sense that, you will not be able to change it, VTHN0 or gamma, by changing the bias or by changing the width of the MOSFET. So what are the things under your control? As once you choose a particular technology, the things that are under your control as a designer are, of course, you can apply any voltages to your source, gate, drain, and body within limits, because note that we have junctions and we have all that. So if you exceed voltages, of course, you can cause a breakdown. So within limits, you have the freedom to apply whatever voltages you want. You also have the freedom. Every technology will say you can use a channel length above a certain limit. A technology defines a minimum channel length. We have been saying 180 nanometer. So the technology is saying minimum channel length is 180. You can use anything larger than that. So as a designer, you can have a MOSFET which is maybe 360 nanometer channel length, double the channel length, or 3 times, or whatever. It's up to you. So the technology allows you that freedom. The other freedom is the width of the MOSFET, perpendicular to this particular plane here. The width of the MOSFET is again under your control. Okay, so the width, again, there is a minimum side to how much width you can use. Okay, we will discuss that later on when we talk about layouts. So there is a minimum, technology will tell you the minimum that is possible. So there's a limit on how small a width you can use for a particular technology, how small a channel length you can use. Beyond that, if you want to use, increase, do as much as you want. Higher values are not a constraint. So voltages, you can apply what you want. Channel length and widths are all available here. The other thing, as I said, these are constants, but these are also temperature dependent. VTHN0 is temperature dependent. 2πf is temperature dependent. So when I say threshold voltage is a constant, if you apply source to body voltage, which is 0, it would appear as if threshold voltage is, if it is, let's say 1 volt here, it would appear that threshold voltage would be 1 volt at all the times. But that's not true. This is only at a fixed temperature. VTHN0 is 1 volt. As you increase the temperature, the threshold voltage would decrease, would become lower. All right, how much does it become lower? That also information you can have from the technology information. All right. Okay, so let's look at this particular picture here. I have 2 MOSFETs, N channel, and the gate and so this is the gate, the drain is here, source is here, and then again the drain and source here. The gate and the drain are shorted together. The gate and drain are shorted together. Threshold voltage is 1 volt. The issue is, will the threshold voltage of the two transistors be the same? M1 and M2. Will the threshold voltage of the two transistors be the same? If they are not the same, whose threshold voltage will be higher? So can you note that this is the source and the body of both the MOSFET has been connected to ground, N-channel MOSFET. Why? We discussed that in the last lecture. All the N-channel MOSFETs are made on the same body, which is the P-type substrate which is there. So all of them have the same body potential. And we said connect the body potential to the most negative point in the circuit. The most negative point for us is ground. So that's why the body is connected to ground, the body is connected to ground. If I apply 3 volts here at the top and ground is here, obviously 3 volt is going to drop as I go from the top to the bottom here. So somewhere here the voltage may be, I don't know what it is, but it would be higher than ground, right? Because the current would flow through this, so it would be higher than ground. So note that the source voltage here, let's say if this is 3 and because suppose I make this statement, watch out if this is true or not. Suppose I say 3, there's a symmetry, both transistors are identical, so the voltage here is 1.5. If it is 1.5 here, so the source is 1.5, this is ground, so source to body voltage is 1.5. 1.5 here, so the threshold voltage of this transistor is higher. While the source to body voltage of this one is 0 here, so the threshold voltage of this transistor is lower. So my statement that this is 3 is symmetric, the voltage here is 1.5. True or not? It's not, there's no symmetry. The two transistors are identical, but they have different threshold voltages, right? So this voltage would be more than 1.5 or less than 1.5? Right now you don't know the current and expressions for current, but the lower the threshold voltage, what would happen? Well, think about it. This would be, if 3, this is 1.3 here. VTHN 0 is, so what I'm trying to show is, these are results from calculations. So for this one, VTHN 1 is 1 volt. For this one, VTHN 1, the threshold voltage of the second transistor is 1.4. So note that when you take NMOS transistors and you stack them, one on top of each other, the lowest one will have the threshold voltage, which is what it is supposed to be, 1 volt. And as you go up, you'll get higher threshold voltages here, 1.4 here. Okay, and if I had another one on top, and then so all threshold voltages of the NMOSs would be different when I stack it. Why this is important? Because when we start constructing gates, when we construct a NAND gate or other gates here, we'll be stacking NMOS transistors. We'll be stacking NMOS transistors, or we'll be and then as we stack, the threshold voltages become different because of different source voltages. So this is important from a circuit's point of view. It's important. If you neglect that, you would be expecting here 1.5, it won't be 1.5. Then you'll simulate to verify, you'll see 1.3 and then wonder where is this one, why is it this 1.3? Well, the answer for that is basically the threshold voltage is source to body voltage dependent. Okay, so that's an important point to keep in mind here. So let's come back. So we're talking about MOS now from the point of view of the model that we want to deploy. So MOS operating regions, very broad operating regions are, one is above threshold. I apply a gate to source voltage larger than the threshold voltage. Somewhere I have VTN, somewhere I have VTHN. These are the same things here. So above threshold is one region, below threshold is another region. Okay. Above threshold, there are two parts to it. We saw the characteristics. There is a linear or a triode region, which is when the voltage applied is less than the saturation voltage. And then there is a saturation part where the current is relatively constant, VDS greater than VDSAT. So what we need is a model or an understanding of how does the current behave here? How does the current behave here? And so these are the places when you look at above threshold, when I use my MOSFET, As I said, above threshold, which means I have significant current flowing in my device. So when I'm talking about MOSFET as a switch, in digital, we mostly look upon MOSFET as a switch. So I'm talking, when a switch is on, so I'm thinking of my MOSFET as biased above threshold voltage. So when the MOSFET has been switched on, when that MOSFET is on, so it could be either in the triode region, depending on the drain to source voltage, or it could be in the saturation region, depending on the drain to source voltage. So this is where my MOSFET is on, in the on state, the switch is on. On the other hand, when my switch is off, when my switch is off, I will have voltage VGS, which is maybe 0, much below threshold voltage here. So I'm somewhere in this particular region. Okay, so both are equally important for us. I mean, this is of course important, the switch is on, but also because remember, when we want the switch to be off, we want the current to be 0 through the switch. We want the resistance of the switch to be infinite, right? But it's not going to be infinite. There will be some current flowing through the switch here. So to understand that particular current, we need to look at this particular region also. Okay, all right. So let's look at how does my current versus voltage expression vary in these regions here. So these are again what I'm giving you are very, very simple equations. Okay? More complex equations, I'll just show it to you a little later. So this is above threshold, this is how the transistor is behaving. Above threshold, IDS versus VDS. The drain to source current versus drain to source voltage. This is how it is behaving. We said this is all the triode or the linear region, and this is the saturation region. So what is the condition for triode or linear region here? Well, VGS has to be greater than threshold voltage, and drain to source voltage has to be less than VDSAT, which is VGS. This is the pinch off point here, VGS minus VTH. If these two conditions are satisfied, you are in this region here. Okay, and the expression for current is in this particular manner. This is how the current is varying. IDS is equal to beta n, VGS minus VTH and VDS minus VDS squared by 2. Okay. Beta n is a parameter, beta n is KPN, W by L. Alright, so let me just write it down. Alright. So now as once you use a particular technology, we've already said VTHN will be given to you, and what will also be given to you is KPN. For a given technology, I have a particular value of KPN. KPN, if you're interested, KPN depends on the mobility, the capacitance per unit area of the oxide which is there, gate oxide, depends on those. But it's not really, from a circuit's point of view, it's not really important what it is made up of, first order. The thing is that this value is given to you. Once you choose a technology, KPN is fixed for you, and VTHN is fixed for you. W by L is something that we vary. That's the thing that is there under designer's control. Changing the width and the length of the MOSFET. This is quite different from bipolar. In bipolar, we never talked about the size of the bipolar. We never said, well, you can make the area of the emitter larger or area of the collector larger. We never talked about those things. While here, in MOS, this is central. Changing the width and the length of the MOSFET. W by L is central to the design of MOSFET circuits. We would change W by L depending on our requirements to different values here. So beta would vary. This beta that you see here, it will vary. This is central to MOS design here. And of course, most of the time for us, VTHN will be constant. And so this is how it behaves. So you can see from this equation that if VDS is very small, the quadratic term would be very small. Quadratic term would be much smaller than the linear term. And that's where the linearity comes in here. Initially, it appears to be linear. That's why we call it the linear region here. But then as you increase the drain to source voltage, the quadratic term becomes more and more important. And that causes the curvature here because it's minus here. That sort of causes the curvature at this particular point. So coming from this here. So many times what happens is, if we are in this particular region here, very close to VDS equal to 0, near the origin here, what we can do is we can simply approximate, we can neglect this particular part. And then you see IDS is beta n, VGS minus VTH and VDS. And so IDS is linearly related to VDS. So the MOSFET acts like a resistor. Linear relationship, anytime you have linear relationship between current and voltage, Ohm's law, you have a resistor here. So IDS linearly related to VDS, you have a resistor. And interestingly, so we are neglecting it, we are looking at it here. So MOSFET is a resistor, but note the value of the resistor you can control by controlling the gate voltage here. Depending on how much gate voltage, gate to source voltage I apply, I'll get different values of resistance here. So MOSFET is in this particular region what can I call it as a voltage controlled resistor. Its value, the value of the resistance you can control by applying different amounts of gate to source voltage. So think of MOSFET as a resistor here, okay, which this particular equation is sort of telling you. Of course, if you go beyond that, then it's no longer like a pure resistor, but a nonlinear resistor it will become. All right, so this is the equation, very important equation, that if I am in this region, then this is the equation that I use to understand my MOSFET operation. Okay. The next part is this one here, the saturation part here. So saturation occurs, again, I'm above threshold, VGS is greater than VTHN, and my applied voltage VDS is greater than VD sat here. Saturation voltage here, which is VGS minus VTHN. So if these two conditions are satisfied, then I'm in this region. And in this region, the current varies as beta n by 2, VGS minus VTHN square, 1 plus lambda n VDS. And we note that this region is not completely flat. It has a small slope that we just saw. This is described by this particular fact, 1 plus lambda n VDS. And the current, of course, is dependent on gate to source voltage. And in this simple model, the current goes as square of the gate to source voltage. IDS is beta n by 2, VGS minus VTHS. So for many of the digital applications, when we are doing quick hand analysis of circuits, we neglect this particular part here. This is 1 plus lambda n VDS, this is small, so we'll neglect this. So what we say is, well, current in this region, saturation region, to the first order approximation, is independent of drain to source voltage. And it varies quadratically with the gate to source voltage. Gate to source voltage, excess gate to source voltage, VGS minus VTHN. Sometimes, you know, this word VGS minus VTHN is called gate overdrive. How much extra voltage you have applied on top of the threshold voltage. So it's called gate overdrive here. So this is the gate overdrive voltage here. So it depends quadratically on the gate overdrive voltage. And beta n is here. All right, so that's saturation. Lambda n is channel n model. So lambda n will also be given to you as a technology parameter. How much does it vary here? So that also you can calculate here. So you can see here the output characteristics of a MOSFET here. If we had gotten more time, we would have done this in 210. So these are slides from 210, but we are having to spend time here. VGS 1.5 to 2.5, you can see how the MOS characteristics. And these characteristics go by the name called output characteristics. Because in a MOSFET, the output is usually at the drain end, right? So it's the drain current. Here, I've not shown here, is the drain current of a MOSFET plotted against the drain to source voltage here. So the characteristics is looking at the MOSFET from the output side. How does drain current vary with drain to source voltage here? So that's the output characteristics of a MOSFET. You can also, of course, talk about how does the drain current vary with the gate to source voltage here, right? So that we will call as the transfer characteristics, because you're looking at current at one end, drain current, and voltage at the other end, right? So we call it the transfer characteristics. So these are, you can see here, these are the points where drain to saturation occurs here. So note that saturation occurs at different points here. VD sat is equal to VGS minus VTN. So 3 minus VTN is 2. So saturation occurs at 2 here. It occurs at 1.5 here and occurs at 8.5 here. So this is our model for the MOSFET in linear and saturation summarized here. These values that I've given, these are for older technology. If you have 0.5 micron technology, very old, 0.5 micron compared to 1. But these are some numbers. I'll give you numbers for more recent technologies later on. So you can see here VTHN for 0.5 micron technology is 1 volt, gamma is 0.7, 2πf is 0.7 here, KPN could be 100 microamperes per volt square, lambda could be 0.01. In most of the, I said L is usually fixed. In most of the digital design, we don't vary L much. We don't try to, whatever is the minimum that is given by the technology, we try to use it, L, this thing. And W, we try to vary. Note that beta, you can vary by W by L, right? So L, sort of keep it fixed. and W, increase it to whatever you want in order to do this here. As I said, most of the time. Okay. All right. Which mode is the transistor operating in? First of all, is it above threshold or below threshold? Above threshold is clear. 2 minus 0.5. Is it so above threshold? What are the choices that you have? Triode or linear or saturation? So where is it? VGS 1.5. So calculate VGS. VDS is 0.2. VD-SAT is, calculate VD-SAT. VD-SAT is VGS minus VTN 0.5. VDS is less than VD-SAT. So it's in the triode region or linear region. This one? Right, saturation. If I take a MOSFET and short is gate and drain, take a MOSFET and short is gate and drain. So imagine if I short gate and drain, this would become 2. Right, so what would it be? Saturation. So always gate drain shorted MOSFET is like a, it's always in saturation. What about this? Quiz question, right? This is a good question. What is it? Subthreshold? Any other answer? I won't put it here if it were that simple. Subthreshold. Yes, the first answer that would come to our mind is subthreshold. VGS is 0.5. VDS is -1. Something seems odd, right? Now, look at the MOSFET here. Look at this particular MOSFET here. When we draw a diagram with an arrow, we are saying this is drain and this is source. But who decides, I mean, in a circuit, which one is drain and which one is source? Which one is drain and which one is source? I mean, how does the MOSFET know that, that which one is source and which one is drain? How does the MOSFET know? Look at the structure is symmetrical, right? So I've been drawing like this here with this arrow and sort of trying to confuse you that this is the source and this is here. But I can take this as the source, right? I can take this as the source. And this is the drain. It seems obvious that this is the source and this is the drain. Drain voltage is higher than the source. That's how we operate here. So then this is 2 and this is 0.5 here. So the transistor is not in subthreshold, but it is above threshold in this case. Okay, the transistor is above threshold. So remember, MOSFET is symmetrical here. You can use source or drain interchangeably. All right, this is what I was talking about. This one is obviously in saturation region. Now note, interestingly, if you look at this particular one, you take gate and drain, short it together. The MOSFET then becomes a 2-terminal device. Right? You take gate and drain, and body is also shorted to source. Okay, so body is not into picture here. Body is shorted to source, so it becomes a 2-terminal device. And it's in saturation region. So the current in a MOSFET then, if you neglect the channel and modulation for a moment, is beta n by 2 Vx minus VTHn square. Right? So how does this look here? The MOSFET is actually operating like a diode. The MOSFET, in this case, you can think of it not like your PN junction diode, but you can think of it like a diode. Why? Because note that for Vx greater than VTHn, above threshold, of course, you have conduction and it goes a square. For VDS less than VTHn, the current is going to be small. So what you can think of is that this is like a diode And diode, we talked about that diodes have turn-on voltage. You can think of it a diode with a turn-on voltage of VTHN. If you go above VTHN, then you get this kind of a characteristics. If you go below VTHN, remember we also discussed that below turn-on voltage is not that the current is zero. Below turn-on voltage also there is a current, but current becomes smaller and smaller, exponentially smaller here. So in this case also below VTHN there is current, but it becomes, as you go below more and more, it becomes exponentially drops. The current drops here. So in the MOS technology, if you want a diode-like function, you could use this. It's not that you can't create a PN junction diode. You can create a PN junction diode also, but you can think of this also as a diode with a turn-on voltage of, depending on your technology, as 1 volt. So for example, if I were to build a rectifier, I can take a sine wave and put it into a circuit like this, and it would rectify. It would give me a half wave rectification, full wave rectification, all of that I can do. Except that it's not a very good rectifier. VTHN is 1 volt, turn-on voltage is fairly high, 1 volt. The other thing bad about this diode is, normally when we turn the diode on, once we cross VTHN, we want the current, current to increase rapidly. It doesn't increase very rapidly here. A PN junction diode gives us exponential rise here. So as you change the current, remember we kept on saying once you go above a turn-on voltage, if you increase the current, well, the voltage across the diode is approximately 0.7 or whatever, right? Why? Because this was exponential. In this case, it's not exponential, it's square. So the voltage, as you increase the current, the voltage will vary. So it's not a very good diode, but it can act as a rectifier. And at many places, people do use it in place of a diode. At various points, if you want diode-like or rectification-like, you can use that here. Okay, so coming back to temperature dependence, that's extremely important again for all our digital circuits. The reason being is that the circuits that you have, we have large amounts of transistors on our IC, very dense number of transistors. And usually to get speed out of the transistors, we also drive it at reasonable currents. And so invariably your ICs are operating at a much higher temperature. They're not operating at room temperature. Your typical high performance processor may be operating at, 70 degrees, 60 degrees, 70 degrees, depending on how the power is being managed, how the heat is being taken off. It may be operating at that particular temperature. Rarely would you find, so it depends. If I open 5-6 applications on your mobile phone, the speed of your chip is going to go up because it's doing a lot more processing. So the speed of the chip temperature will go up. If you have only one very weak application on, the chip temperature may be very low. So depending on how you are using the processor, how much power is being consumed, your chip temperature may go up to 60, 70, 80 or whatever it is, or it may be even room temperature here. So note that temperatures are varying. Your IC temperatures are varying. And as the IC temperatures are varying, the MOSFET characteristics will change. And so it's important to understand how does it change here? What happens to a MOSFET when I change the temperature here? So look at this current here, expression for current in saturation. There are two important things that are there in this particular expression here. One is VTHN, which is temperature dependent, and the other one is KPN. These two are temperature dependent term, WL and all that are obviously temperature independent. KPN has mobility in it. If you recall, I just briefly showed you an expression, mobility. Mobility is highly temperature dependent, and VTHN is also temperature dependent. So what happens is, generally, both KPN and VTHN, they decrease with temperature. If you are at room temperature or above, KPN will decrease with temperature, mobility will decrease with temperature, and VTHN will also decrease with temperature. So things are not as simple, because a decrease in threshold tends to increase the current. If you bias it at a fixed gate to source voltage, a decrease in threshold will try to increase the current. While increase in temperature causes a decrease in KPN, so that causes a decrease in current. So the answers are not very simple as to what really happens to current, because one term is decreasing, the other term is actually increasing. Okay, so that again, I'll not make absolute statements at this particular point. I'll just illustrate. If I am, so this is again for my 0.5 micron technology. Look at the condition that I'm showing. 1.2 volts. When I write 2 by 1, what does it mean? Width of the transistor is 2 micron, length is 1 micron. So the ratio W by L is 2 by 1. This is at T equal to 25 degrees Celsius. I am applying 3.3 here. The current is 20.28 microamperes. By the way, when we come to our MOSFETs, most of the time get used to currents would be in microamperes. In bipolar, most of the time we were in milliamperes current, right? So here you will see most of the time microampere current here for typical sizes and all that. So 1.2, 2 by 1, 3.3, 20.26 here. Same 1.2, same bias condition. The current is at 50 degree, little higher, 23 here. Note here, 3 volt I apply, 3 volt I apply, 25 degree 0.41, and 3 volt I apply is 0.39. Don't go too much about the numbers. The numbers would be smaller, right? The number, all that is indicating is that the current would be smaller here. So what I'm trying to illustrate is that when you go towards lower bias, when the bias voltage VGS becomes smaller and closer to VTHN, what happens is at that particular point of time, this term may be more important. VGS minus VTHN. See, VGS is, if it becomes very close to VTHN, then any change in VTHN will have a strong impact on IDS, right? And KPN always has the similar impact. While when VGS is much larger than VTHN, even if this changes with temperature, well, VGS minus VTHN may not change that much. So what I'm trying to say is that as you go towards higher voltages, when you apply higher voltages here, the current is with temperature likely to go down. Current will go down. So yeah, so if you have certain current at 25 degrees Celsius room temperature, and your IC, let's say you turn the MOSFETs on, and your IC turn the MOSFETs on, and the currents in a MOSFET would be lower at higher temperatures here. So remember, we are talking about MOSFET being on or off. So when it's on, is, you know, if my supply voltage is 3 volt, I'm going to apply full 3 volts to my gate here, right? So at that particular point, you may find currents are smaller. So this is at 50. If I go to 70, current may be even smaller here. So generally, as the temperature goes up, the currents are going to be smaller, lesser. And lesser current in general means, as we will see when we analyze, lesser current means, you know, all the speed problem comes about, performance comes about because I have to charge and discharge capacitances. So when I have less current available and capacitances are the same, capacitances are more geometrical parameters, dielectrics and all that. So capacitances remain the same and I have smaller current here. So I have less current available to charge and discharge the capacitors. So my performance goes down, delay increases and all that. So remember, if you open up 5 applications on your cell phone, your chip is going to get hot and it's not going to run very fast. And the reasons for this are your MOSFET has become slower. The currents have become slower. One simple reason. There are many other factors that are there, but I'm saying your MOSFET has become slower. At 70 or 80 or 90 degrees, your MOSFET is slower. It carries less current as compared to at lower temperatures. So all that I'm trying to illustrate is that temperature dependence is important. As a designer, so these are for 0.5 micron technology. For other technologies, the numbers and all that will all change, and one has to do the calculations. But it's something to be aware of. Okay, what happens to my this thing? So on the other hand, this is also telling you the following: that as I go to lower temperatures, my currents are going to increase. Right? So why don't I operate my if you really want very high performance circuits, why don't you take your circuit and put it in where? To get lower temperatures? Refrigerated, right? Put it in a refrigerator, right? Put it in a refrigerator. Now, refrigerator means what? Not your big refrigerator, right? So if you take your MOSFET and put it in a very nice way of reducing the temperature of a MOSFET is to take it, the whole chip or whatever is there, and put it into liquid nitrogen. Liquid nitrogen, what is the temperature? Kelvin, what is the temperature? 77 Kelvin. So very low temperature. And you put it in liquid nitrogen, your currents are going to be higher. And the currents would be higher, it would operate at higher speed. So if somebody, let's say, is really wanting, making a supercomputer or whatever, and wants very high speed, so their cooling and all that becomes very important. If you have air cooled or water cooled or whatever it is, if you can lower the temperature, lower temperature would imply better performance from your MOSFET. All right. So back to now the last one here, above threshold, saturation, triode, and let's look at subthreshold here. So now what I'm plotting is the following here: drain current versus gate to source voltage. So this is what we call as the transfer characteristics. The first one was output characteristics. This is transfer characteristics. So transfer is drain current versus gate to source voltage. So note that we have a current here. I'm plotting it in saturation. I'm applied a large drain to source voltage here. So note that this is where I have threshold voltage here, 1 volt. So above threshold voltage, you can see current increasing quadratically. VGS minus VTN square. Quadratically, it's increasing. But once I go to threshold voltage and below, it appears the current is 0. And the linear plots, keep in mind, linear plots are very, very misleading. Linear plot, when you plot a current and a voltage on a linear scale, is very misleading. It says current is 0. So when you have that, the best way to see this is on an exponential scale here. So this is our saturation, this is a subthreshold. So same characteristics plotted on a subthreshold. On a log. This is log, and this is still linear. So semi-log plot, and threshold voltage is somewhere here, VTH in here. So note that this is our saturation region where the current increases quadratically. So a quadratic increase in current on a log scale appears to be as if it's not increasing much on a log scale here. But below VTN, look at how the current is changing. There's a transition region here, but then if you come here, the current is a linear plot on a semi-log, a linear line on a semi-log plot indicates it's exponential. So the current is reducing exponentially with the voltage here. Right? Exponentially reducing voltage. This is the nature. This is the subthreshold characteristics. So simply going a little bit below VTN is not going to decrease the current a whole lot. If you want your MOSFET to be really off, you have to go to lower and lower voltage here. And I've not plotted here. I've plotted from 0.2 and all that. But note, even if I apply 0 volt here, there would be a current flowing through the MOSFET. If, drain to source voltage is whatever here. So for the time being, suppose that this is not 0.2, this is 0 here. So I have a leakage current flowing through my MOSFET, maybe 1 picoamperes. And VTN is 1 volt here. Now imagine that I take this whole characteristics and I shift it left. I take my MOSFET, the whole characteristics, and I shift it left. What would happen? Shift it left. Why am I shifting left? Now the whole thing is operating, let's say this is 0 and 2 volt. So my whole range of operation is 0 to 2 volt. Now I have a new technology with very small channel lengths and I shift the whole characteristic. Now I don't want to operate at 2 volt, I want to operate at 1 volt. The whole circuit to operate from 0 to 1 volt. So I shift this characteristics whole towards that particular range. What would happen? Imagine scaling from 0 to 2, the whole thing scaled to 0 to 1. Compressed it to 0 to 1. If I simply scale it, if I start shifting it, let's say VTN is 1 and when it is 2 and I make VTN equal to 0.5. I scale VTN to 0.5 here. And the characteristics, the shape remains the same. Maybe you can see here that as I go VTN 1 to 0.5 here, the curve will shift like this. And what will happen to the leakage? Leakage will increase. So this is an extremely important thing that happens when you try to scale, because as you scale the MOSFET, we'll see later on, as you scale the MOSFET, you have to scale the voltages also to manage the electric field in the system. Because if you simply scale the channel length and without scaling the voltage, the fields become very high and the transistor characteristics are no longer proper. So as you scale, you also have to scale the voltage. And as you scale the voltage, you'll have to scale the threshold voltage also. So these characteristics shift left, and what you start getting is increasingly more and more current here. Okay, let's start.